Hi everyone, and I'd like to introduce a nice application of the half-angle formulas in this video. So I stated this half-angle formulas here, cosine theta over 2 and sine theta over 2. So if you know the cosine theta value, you can calculate half of these angles, not the angles, but the cosine value of that half of that angle, sine value of the half of that angle. This is derived from power lowering formula or double angle formulas. So let me show you the application and idea that goes into this application. This is a copy from my notes, and I'd like to explain the idea using this one. So this value here is 1, 0, therefore cosine 0 value is 1. And that one here is 90 degrees, as cosine 90 degrees is 0. That's in some sort of extreme to the right and to the towards the north of this unit circle, so it's really easy to compute these two values. So I'm going to explain later, easily using this half-angle formula and addition formula, you can easily calculate the cosine of the angle right in between in here. This is 0 degree, that's a 90 degree, and then right in between, the angle will be 45 degree. Well, many of you already know the cosine 45 degree is exactly 1 over root 2. If you use that half-angle formula, you will just derive that without using the right triangle with the 1, 1 root 2. Just that half-angle formula, and you can arrive here. Idea is keep doing this. But now we have originally with a simple value 1 here and 0 there. Now I'm claiming that using that formula you can get that one. So we have these 3 points. In between the first 2 points, you can calculate using the half-angle formula, and you can calculate this cosine value, which is cosine of 22.5. And these 2 points, right in the middle, I remember that was a 67.5. So cosine of 67.5 can be exactly computed using this exact quantity 0 and 1 and 1 over root 2. So now you have 1, 2, 3, 4, 5 values, and we have a full exact control on those values. We know exactly what those values are. So with that, you can apply this idea again. Since we know these two, use the same mechanism to compute the angle and right here, and an angle right there in between, and there. By continuing doing that for 10 times and 20 times, you can imagine we have a lot of angles in here whose cosine values is exactly calculated. We're probably not very interested in exact values, but if you turn those into a decimal expansion, doesn't matter 100 decimal places, 200 decimal places, since we have exact expression, we can get those values and very, very precise and exactly. Since we have those values, anything in between that we didn't touch can be approximately computed using this thing, and that's the idea. Now let me introduce this additional formula, which is the following. If you have angle theta 1 and theta 2, which was at the beginning was 0 degree and a 90 degree, but you're going to have more and more angles. Then we're in the intermediate step, we have one angle and another angle, and we know the cosine values of each of them. The angle right in between theta 1 and theta 2, by midpoint formula, or average of that two angles, going to be exactly in the middle. So that's the angle. And we want to compute that cosine value of that angle if we know cosine theta 1 and cosine theta 2. So here's another idea. You can split that sum, and you can write it as a cosine of one angle and plus cosine of another angle. Then you can apply addition formula. Then it's going to be cosine values, sine values of that half angle. Then we can apply this half angle formula. So here it is. This is the addition formula of cosine of the first angle times cosine of the second angle, minus product of the sine. So now it's time to apply this half-angle formula for each of the spot in here. Then we can use the knowledge on the exact values of a cosine of theta 1 and theta 2. So it's down there. So substitute this one with this half-angle formula version. So cosine theta 1 appears there, theta 2 appear there. Sine theta 1 over 2, have this version with the minus theta 1 appears there, and sine version for the second factor appears down there. So here's the formula. We're going to repeat this over and over. We're going to start with the 0 and 90, and we're going to apply that to the 45 and 90, which will be, this one will be 67.5. Then you can apply 45 and 67.5, whatever the combination, and we can calculate this exact way. There's going to be a lot of nested square roots, and no one wants that, but at least you know it is very, very accurate. Whatever the decimal approximation you choose, you know it is all the way down to the accurate for those values. We'll be back to the different layers. Let me introduce this idea. This is one picture I'd like to show you. This is at 0 degrees vertically. I plotted the angles to show you this mechanism. 0 degree here, and up there is 90 degree. And this orange color line is where the 61 degree is. So if our goal is calculating cosine value of a 61, we're going to repeat that algorithm, averaging cosine value of average of the given two angles in the following sense. We're going to start with 0 and 90 degree, and we calculate 45 right in the middle, and decide whether the 61 degree fall in. Is at the first half, 0 to 45, or second half, 45 to 90. And here you can see we want 45 to 90. Now you do this process again to narrow it down to the 61 degree. So we're looking at 90 and 45, and you consider the midpoint, half of it, and decide whether 61 falls in the first half of the interval or second half of the interval. And here it falls in the first half of the interval. So you choose this bottom point and the midpoint, not the midpoint and the one above. So we narrow it down. We know it's in between in here. Repeat this process again. You look at the half point and figure out which interval it belongs to. This time it's upper interval, so we're going to choose the midpoint and the higher one. By keep doing that, we guarantee that these 2 points we have will narrow down to very, very close to 61 degree. And in each step, we are applying that method that I just introduced. We have two cosine value already calculated. Then you can calculate this midpoint cosine value and that point cosine value. So if you repeat this method several times, you could have these two cosine values that are very, very close to each other. And because 61 is always in between, that is going to be a good approximation of cosine 61 value, degree. Sorry about changing the color abruptly like this, but this is my Mathematica animation. This time I'm showing the 32 degree. 32 degrees down there. We're starting from 0 to 90 degree, and you can see how the choices have been made. So by the time it's here from this scale, you can't really see much the difference in here. So, and we know this value which is supposed to be very close to cosine of 32 degree. So I think the idea is clear, and I'm not going to explain this Mathematica code to do that automatically, but you can see that here I'm calculating that formula. This is a cosine part and that's a sine part. If you happen to have two values, and we're going to just repeat this one over and over. The rest of the part is just computer programming language to do that. Then I'm going to explain the second part of these calculations, something that we definitely have to think about. Before we go into the next discussion, let me make sure that we understand why we're doing this and think about back then and how people would computed the correct value of a cosine to arbitrary precision. Before we having a calculator, even in these days, those people who have creating the calculator, how do they know all those values? This is one way. This is probably the ancient method, but it still works. And these days, there are better algorithms. But the merit or virtue of going through all the things like this is not the practical purpose, is to understand the mathematical idea and how we approach problems. Suppose this is something that is unknown, and it clearly shows you how to approach a problem. And that I think is a good example for that. So that's why we're doing this. The second question I would like to ask is that the value we have calculated is actually perfect for those angles which happen to fall into this shape. But for example, like a 61 is not going to be exactly in that shape. 61, for example, 61 degree is going to be in between these A and B we know exactly. But 61 might fall in between in here. And we have a good approximation. A and B is almost the same, and C is trapped in between. The question is that how many digits that we get? We don't actually know this one. We think if C fall into this correct value A and B, A or B is a good approximation. So let's say, not knowing what the C is, whether it's close to that or close to that, I'll just go ahead and say A is the correct one. So that's my algorithm actually. You go divide this one, keep doing this many times, so that we narrow it down to this cosine value and that cosine value, and just say that that cosine value we're actually looking for is almost A. But the question is that if you want an accuracy, how many digits of that thing, that C, which approximates with A, is correct? Here's one easy answer. Because we're doing this many times, dividing into two pieces in half in a lot of times, this A and B is almost equal. So there are many digits, let's say n digits, decimal places are already equal to each other. Then you can conclude that n decimal places is actually the correct n decimal places of a C. So I'll give you an example. So if A is 0.23456 and C is 0.23478, and we don't know what C is, but because this 234 and 234 is common, if you think about it a little bit, you can easily conclude that the number C must have the same three digits, 234, like this, and we don't know this one. So my program will just not actually compute C, but claim that the C is actually approximates this value, and then determine using the program which of the two digits in here, and I have this is exact value in my algorithm, that's absolutely correct value, and think about the common digits and claim that that value that we're calculating at least have this digit's decimal place is correct. So I think the idea is simple, but when you write a computer program or doing things like that automatically, we're not going to look at each of the data and figure out which are the common digits and things like that. So I'd like to, this is a neat common algorithm to determine which of the digits are correct. I mean the common. So here's an idea. What we're going to do, we're going to subtract these two numbers, B minus A, and because of these common decimal places, you can have lots of zeros. So we want to count how many zeros are there using a little bit of a trick. The idea is using the logarithm. So B minus A is written like that so that we clearly relate to the number of zeros, but this happened to be the engineering notation for a number, so I will do the calculation with this expression. So what we want is a 3, but if you write an engineering expression like this, we happen to have -4 in the exponent of 10. So if we start from here as a 1, 2, and 3, and 4. So you have to multiply 10 to the -4 if we write this magnitude part with a 1 decimal and dot and rest of the part. Right, idea is that if you hit this one with a logarithm 10, base 10, we're going to capture that number nicely. That number is very closely related to 3 that we're looking for. So here's the next step. that product inside the logarithm becomes the sum. So here's -4, that's exponent, that's through the logarithmic law. 2.2 stays inside. Because this number is always less than 10, this is going to be always number less than 1. That's how the logarithm works. So now if you add a positive number to -4, that is going to be -3 times dot and whatever the rest of the number is. So this number, if it is 3 zeros, 3 common decimal places, and it is appearing as an integer part, magnitude of an integer part of this quantity. So what we're going to do, change that sign to positive using the absolute value and drop those decimal places. That you can do using computer programs. This is not a standard name for a mathematical function, but in most of the computer program language, it is a thing to do to drop this decimal fractional part. So putting absolute value, change that to positive number, and drop that fraction, becomes 3. So this function, if you're looking at A and B, and if you hit that one, it's going to give you an integer number, positive integer, that will measure or count number of decimal places that are equal in the for a successive sequence. So in my program, here's my cosine value, and I will calculate that cosine value using that estimate, which is the half of all those angles, and measure exactly how many decimal places are correct using this function, and only show the correct decimal places. So here's some values I calculated using that algorithm. Think about that. You are creating this table for manufacturing electronic calculators, things like that. So this 50 means I divided the 0 to the 90 degree in 50 divisions. If you do 1, you create a 45 degree. If you do it 2 times, you create 22.5 and 67.5. So we're doing that 50 times. Then my algorithm determined how many digits are actually decimal places are correct, and only show the correct decimal places in here. So starting from the degree 1, that's the cosine value, ending it here, cosine 30 degree being this value, things like that. Like I said before, the thing about this whole video is the idea. First, look at this algebraic relationship between the values we're calculating, and using that we're able to approximate any values of a cosine using this mechanism. So that's the important idea to learn.